Welcome. Let's solve Leetcode 2872, maximum number of K-divisible components. All right, it's kind of a long one, so as far as the prompt, but let's go over it. So we're given a tree, it's undirected, and they define something called a valid split. Let's make this bigger. A valid split of the tree is obtained by removing any set of edges, possibly empty, from the tree such that the resulting components all have values that are divisible by k, where the value of a connected component is the sum of the values of its nodes. Return the maximum number of components in any valid split. One thing that we know for certain is that they tell us that the input is, sorry, this is what I wanted here. The sum of the values is divisible by k. So we know that there will at least be one component, at the very least. Okay, so let's kind of go over what they mean here. So let's look at this example here. So we have this tree, and here are the edges, which correspond to this graph, 5 nodes. And so what we want to do is we want to look and determine if this tree can be somehow split into smaller trees, or even where a single node is also considered a tree, such that the corresponding value for that component is divisible by k. So let's look at this one here. So here they call this 1 and 3. These nodes are called named 1 and 3. However, they're really nodes 0 and 2. So here we go. Sorry. Yeah, 1 and 3. So 0 and 2. Yes. Oh, my mistake. Sorry. This is okay. So never mind. It is 0. So they start off at 0. So 1 and 3. So 1 and 3 are values 8, 0, 1, 2, and 4, which is 12. When you add them up, you get 12. 12 is divisible by 6, so this is one component. 1 and 3, if we remove the edge from 1 and 2, 1 and 3 are perfectly fine. And I think we could just assume mathematically that the other component will work, but we can just go ahead and verify it. 0, 2, and 4, so 0 is 1. 0 has a value of 1. The second node has a value of 1, and the fourth node has a value of 4. So summing all of those up gives us 6, and 6 is divisible by 6. Hence, there are two components that are each divisible by 6. Okay, so that would be the answer. All right, I think this second example, okay, is pretty much similar, so we don't need to explore it. We can just kind of jump into it. Okay, what we're going to do is we're going to use recursion and depth first search, and what we'll do is the question is, what will our recursive function do? So let me go over this example here. So we will use depth first search, where this function will return the value, return the remaining, the value of itself and itself and its what's the word, and its member nodes. Let me see. Value of itself and other nodes in the same component. So for example, what I mean by that is this. So this 2 would return the value of 6, 2, and 5 here. And this node here would return 1, 4, and 3, and this node 0 would just return itself. My point is, every time we call this function, it's always going to return the value of itself and its member, other members of the component. Okay, so let's see how that'll help us. So I've drawn this example here. I know it's not the best visually, but my point is it satisfies what we're aiming to understand. Okay, here we have 2. Now, one of the first things for our function is when we call this DFS function, we'll just call this, I'll just call this 2 for the value 2 for this node. This is well, I'll just call it node here. So what we'll do is we'll set the current value of it. So we'll say something like total equals value of the node. So in this case, you can see that it's 2. Okay, so it's 2. Now what we'll do is we'll loop through the neighbors, loop through neighbors, and ask ourselves the same thing. Loop through neighbors, and determine if divisible by k. So let's suppose we start at this 4 here. Let's switch it around just to make it easier. So if we started this 4 here, and just suppose k is 4. Just suppose k is 4. So if we're looking at this node, so first we go into 2. So right now the value would be here. So the value would be 2. And so our first, so neighbor 1, neighbor 1, which is 4. 4 is divisible by k. So that means we increment number of components. Okay. And then we do the same thing. So let's do this here. And then we'll do the same thing for 4. So neighbor 2. So just to be clear, these numbers here don't represent like the name, they represent the value. Because that's the name is not really important. We just care about the value. So neighbor 2, 4 is divisible by k, so then we increment the number of components again. Okay, great. So every time we look at this, we're always looking at just that node, its return value. Remember, it will return the value of itself and any nodes in the same component. So this node has no other, but beneath it, there are no other members or other nodes that belong to the same component. Same thing for this 4. Now let's look at this 2 here. So for neighbor, let's put this here, neighbor 3. Let's copy this down here. So neighbor 3 is, so 2 is, so this is the return value. So 2 is not divisible by k. So 2 is not divisible by k. So then it moves up to the parent node. And then it'll say, okay, well, we're done. Meaning like we can't, there isn't more to explore. So what do we do? Well, what we do is, remember, we return 4. Well, why do we return 4? Well, we return 2 plus 2. Remember, because we return the value of itself and other nodes in the same component. So we return 2 plus 2, which is 4. So at the end, so once we have returned, we check if the return value is divisible by k. If yes, increment components. Else, do nothing. Well, do nothing. So I hope that makes sense. So we started with this node here. Then we said, okay, we're going to use recursion. So we go to the 4. 4 is divisible by 4, and we don't need to go any further because there are other nodes. Same thing for this 4. We see that this is on its own. This node by itself is perfectly fine divisible by 4. And remember what they want us to do. They want us to return the maximum number of components. And a single node is a component. So perfectly fine on its own, perfectly fine on its own. This node needs help. And it just so happens to be that its parent also needs help. So 2 plus 2 is 4, and then they are both divisible, but when added together, they work out just fine. So in this case, the answer would be 3. Let me go over one more adjustment here. So what if this was a 1 here, and let's maybe modify this a little bit, make this a 1 here too. So again, these two nodes are perfectly fine, so let's just kind of focus on this here. So if we go to 2, 2 goes to 1, and then 1 looks at its children or its neighbors, and it sees 1, and 1 says, well, if we're looking at this one, we'd say neighbor 3. Let's kind of go show the recursive how it would look. So neighbor 3 has a child here, so 1 here. So 1 is not divisible by k. So then we go back to 2. So go back to 1, which is its parent. And then we say, okay, well, this one and this one are still not divisible by k. So then we go back. So when we go back, though, remember we're return the value of itself and the other nodes in the component. So we return 2. So we return 2, return value 2. And then, okay, so then we're up here now. And then, so we add it to itself. So 2 plus 2 is 4, and then we just continue on, and then we will just return 4. And then we return 4. And then whoever called this function that here, or whatever called it, we check that final check. Just like we do here, we check if it's divisible by k, and we increment the number of components. We do the same thing on the outside. So even though in here we're doing it in our function, recursive function, we're going to do the same thing on the outside, wherever it was called. One last thing, though, is that, remember, though, when we go to 2, so 2 is always saying, okay, check the neighbors. But 1, when we go to 1, though, the neighbors of 1 are 2 and 1. So, but remember, though, we just came from 2, so we don't want to end up in an infinite loop. So we'll need to do something to prevent that. So when we're writing our DFS function, we'll have a parent here, and we'll always check if, and then we'll say skip parent. So when we loop through our neighbors, we'll skip the parent. So if we're at this guy, we're only looking down in this respect. We're not looking at the parent. Anything above we don't care about. We want to look down. Okay, I just want to make that point. Okay, I think that's enough to get started, so let's do it. And if anything's clear, I think it'll become clear once we start coding this up. So what we'll do is maybe we need to create our graph. So let's set up g equals default dict. Let's make this bigger if we can. Yeah, here we go. It's default dict, and then we'll make it a list. So this will store the neighbors. Then we'll say for u comma v in edges. Then we'll say g of u dot append v, and do the same thing for u. Okay. And then we'll say let's just print g, so we got to look at it, and just in order not to throw an error, we'll just return 1. Let's maybe make this smaller, and let's run it. I just want us to see what g looks like. Okay, it's fine. So g. Okay. So notice 0 is connected to 2. So let's open our that's fine. So 0's connected to 2. which is fine. 0 is connected to 2 here. 2 is connected to 0, 1, and 4. So 2 has 3 neighbors. 1 has 2 neighbors, which are 2 and 3. Okay, and 3 is connected to 1, and 4 is connected to 2. Yeah, can't see that, but it's there. But then trust me, it's there. Okay. Okay, so let's go back. I just wanted to show you how it looks so far. Okay, so then let's carry on. So now we, what we'll do is we'll call, well, let's do something here. We'll call let's call DFS. We'll call that function. And for now, we'll set it equal to 0. I do have an optimization at the end that will be interesting. And then we'll call, and then we'll return. Remember though, what do we say down here? The DFS will always return the value of itself and other nodes in the component. So this will return something. So let's just say maybe, I don't know. So if, so we'll call this maybe, let's call this components equals 0. So if this is divisible by k, then we'll say components plus equals 1. And then we'll just return components. So remember DFS, the way we set it up, it always returns the value of itself and any other nodes in this same component. So remember, if we start with this node, we'll return 4, and we wouldn't know if that was divisible by 4 unless we do this here. So I want to make that point here. Okay, so you probably see a couple mistakes already made. First one is that we need to indicate a parent. So for example, we'll just say at least this node does not have a parent. And now let's define our function. So define DFS, and we'll call this node and the parent. Okay, so what do we want to do? Remember we set a total equal to the current value. So this is the node itself. So total equals the value of node. Remember that they give us this values array that stores the value of the node. And where are we at? Okay, then we want to loop through the neighbors. Okay, so let's do that. So for neighbor in G of node. Okay, great. Now remember, we wanted to skip the neighbor if we came from there. So if neighbor equals, or just not equals to parent, we'll do this. So we'll say, okay, what do we want to do? We want to say, well, yeah, it's fine. So if we want to call DFS on the neighbor node, and now in this case, the parent of the neighbor would be node. Okay, and I'm going to call this subtotal. So what we're doing here is we're checking if we're going to 4, we're checking if this 4 or in this case 1 and 1, if that node by itself or any sub nodes that it visited, if that is divisible by k. If it is, then we can increment components. So if subtotal is divisible by k equals 0, then we say, okay, components plus equals 1. Otherwise, we're going to add you to the total. Subtotal. And then we return the total. Now I purposely made a mistake here. Let's see if I'm going to run this right now. And I want to see if it throws an error. Okay, sorry, did I spell it wrong? Oh. I think this is values with an S. Sorry. Okay, that wasn't the mistake I was talking about. All right, perfect. Cannot access local variable components. So there's a couple ways of doing this. So I would like this variable to be the same as this variable. What I'm going to do is, some people can use a global, but I'll just call this self.components and self.components, just to make it a little bit easier or cleaner. And I think it's fine. It's a little bit long for me, but we'll just go with it. I want to run it now. Okay, so was I supposed to run it now? Sorry. Okay, did anybody see where I made a mistake? So it's right here. So we want to make sure it's divisible. So that means we want to check if it's 0. And then that should work. Okay, let's submit it. And I do have a slight optimization, and I wanted to point it out to you. Okay, so it works fine. I don't know if this is an optimization, but I wanted to go over something, a couple of things. So let me rewrite this here. What I'm going to do is I'm going to say something like, okay, I'm going to write this in one line. So return, yes, so this is self.components plus 1 if that else self.components. So let's see if that's correct. Let's just check it. Okay, I think that's fine. Now this is something I thought of. Now remember, we're dealing with a tree. So let's go over this here. So we're dealing with a tree. So for some reason, like, why do we have to start with 0? There isn't really a requirement that we start with 0. We can start with any node, really. The only thing is that sometimes, in this case, they only have one node. They only have one node, so I can't start with. I can't just put, for example, I can't just put 5 in here. I don't know how many nodes there are. But what I'm going to do is, in order just to like mix it up, I'm going to say n divided by 2. So if there's 10 nodes, I'm starting at node 5. My point to you is that it's a tree. This is a tree. It doesn't matter which node we call the root node. It should still work. And so I wanted to make that clear at the very least. So let's I guess we could just submit it now. And it might not make a difference, but it's more about interesting knowledge that you should be aware of. So let's submit it. Okay, so it was a little bit better. So my point to you is that it shouldn't matter which node you start with, because this is a tree. It should work with any node you start with, and it should be fine. Okay, if you found this in any way helpful or educational, please consider liking or subscribing. Other than that, have a wonderful day. Take care of yourself.